Okay, so question number 4. A beaker in air contains a liquid. The base of the beaker is contact with the liquid and there's area A as shown in Fig 4.1. So if you start the diagram, you can see what has just been said. The liquid has density rho and fills the beaker to a depth h. By using the definitions of pressure and density, showed that P is equal to rho GH, where P is the pressure due to the liquid and that is exerted on the base of the beaker. So first things first, we are told that by using the definitions of pressure and density, this there is the definition of pressure, this there is the definition of density. Now, we know that the pressure is force over area. So what is the force due to the liquid at the bottom of the container? The force on the bottom of the container due to the liquid is actually the weight of the liquid. So we go around looking for weight. Weight is equal to mg, mass of the liquid, times the acceleration due to gravitational field strength. But do we know the mass? That's when the density equation comes into place now. We make mass subject of the formula. Mass is equal to density times V. Then we come here, where there is mass, we substitute mass rho V. But we also know that we don't know the volume of this liquid, because V will be the volume of the liquid. So volume of the liquid will be calculated by multiplying the area of the base of the container multiplied by the height, by the depth of the water, which is V is equal to AH. So where there is volume now, we are putting AH, which gives us this. So our weight is equal to rho AHG. That's our weight. So now pressure, remember, is force over area. So where there is force now, we are putting rho GAH over the area here, like that. So the area cancels out, we get rho GH. So to the next question now. The next question, the question says, suggest why the equation in A does not give the total pressure on the base of the beaker. The reason why it doesn't give the total pressure at the base of the beaker is because there is also, when we put a liquid in air, especially with the surface, top surface open, at the base of the liquid, there is pressure due to the liquid, but there is also pressure due to the atmospheric pressure. The atmosphere pushes down. The atmosphere pushes down onto the surface of the liquid. Therefore, at the base of the liquid, we have pressure due to the atmosphere and pressure due to the liquid. That's why the total pressure is not just due to the pressure of the liquid, which we found in A. The equation in A just finds us the pressure due to the liquid. Fig 4.2 shows the variation of the total pressure inside the liquid with the depth x below the surface. So determine the density of the liquid. We have to understand some few things here. For starters, when x is 0, x is the depth of the liquid, so starting from the surface. So when x is 0, that's when we are at the surface. So the pressure that we are only having here in that case, which is 960, will be the atmospheric pressure only. So as we go deep into the liquid, for example, when x is 8, the pressure of 966 is the atmospheric pressure plus the pressure due to the liquid. That's why the pressure is changing. So we can write that in the form of an equation by saying total pressure in a liquid is equal to atmospheric pressure but plus the pressure in the liquid. And to simplify it, we can say total pressure being PT is equal to PATM, the pressure due to the atmospheric pressure, plus liquid pressure, which is rho GH. Now we make rho subject of the formula here by taking P atmospheric pressure to the other side and dividing by GH. So we now have rho, and we substitute into the equation. For example, when the depth is 8, when x is 8, then h is 8. So our h will be 8. So 8 will be 10. 8 times 10 to the power of minus 2, because it is in centimeters, we must convert it to meters. Then G is 9.81. Then this is the pressure corresponding to the depth of 8. I could have used 7, I could have used 6, I could have used 5. Then this is the pressure at the surface. this will give us an answer such that if you round it off to two significant figures, it will give us 7/7. So we write our answer as 7/7, like that. So then we go to the next step now. It's important that we understand here. We must understand that as we read the question, some logic which the question is saying. Firstly, the question says a cylinder is held stationary. When something is said to be held stationary, they mean that it is in equilibrium. What do we mean there? We mean that something is in equilibrium, meaning that the forces acting on it vertically and the forces acting on it horizontally are all equal. So that object is in equilibrium if the forces acting on it vertically and the forces acting on it horizontally are all equal, such that the resultant force on it is 0. So when something is said to be held stationary, it's also not rotating, meaning that the resultant moment is also equal to 0. So this object is in equilibrium. That's what they're implying. So that the base of the cylinder is level with the surface of the liquid. Now, if the base of the cylinder is level with the surface of the liquid, then the cylinder is not inside the liquid. So according to the forces that were shown here, there is the force due to the tension, as I read. The cylinder is length, that one, 4.0 times 10 to the power minus 2, and the cross-sectional area, 3.7 times 10 to the power minus 4 square meters. The tension in the wire is 0.53. So we are not shown any other source of force except for the tension in the wire, which is a force going upwards. So there must always be also another force going downwards, which we know to be the weight of the object. Every body has a weight, and weight acts from the center of gravity. Sorry for the arrow is not proper there. Yeah, so there is a weight going downwards. Now, since the question has said that this object is in equilibrium, then the forces acting upwards must be equal to the forces going downwards for it to be in equilibrium. So this statement was given to you so that you would know that the weight is actually 0.53 newtons. So next, now the cylinder is now lowered, then held stationary. It's always lowered. It's lowered into the liquid and held stationary by the wire so that the top of the cylinder is level with the surface of the liquid. Calculate the new tension. So this diagram here represents what we're talking about. It is lowered, the cylinder. This here is our cylinder. It's inside the liquid. So if the cylinder is inside the liquid, as it has been lowered, then the weight, of course, is to 0.53 newtons going vertically downwards. Weight doesn't change. Weight is equal to mg, and as long as we're on Earth, the g is 9.81, the gravitational field strength g. Then so weight remains constant here, but there is a new tension. That's why they're asking us to find the new tension. Why is there a new tension? Because for this object to remain in equilibrium, to be in equilibrium, considering that the vertical force going downwards is the weight, when a liquid is put into water, then there is another force that will be acting upwards on the liquid, which is called upthrust, according to Archimedes' principle. So that's why you can see here, there's now, according to what I put here, upthrust, and there's tension. So the tension can no longer be the same if the tension and the upthrust are supposed to be equal, 0.53. So that's what we write here. Tension plus upthrust equals 0.53. Then a tension, we make a upthrust go to the other side, then tension is equal to 0.53 minus U, which is the upthrust. But U, the upthrust, is equal to rho GV. This you must always know. Who is rho? The density of the liquid. Who is V? V is the volume of the liquid displaced. But how do we know the volume of the liquid displaced? Who has displaced the liquid? The liquid has been displaced by the cylinder that you have put into the liquid. So the volume of the cylinder is equal to the volume of the liquid displaced. So we will look for the volume of the cylinder because it is the cylinder which has displaced the liquid. So the area or the volume that is now occupied by the cylinder was once occupied by the liquid. So in other words, the total volume occupied by the cylinder is the volume of the liquid that was occupying that particular area. So V is the volume of the liquid displaced, but we find the volume of the cylinder to find the volume of the liquid displaced. So now we are now saying 0.53 multiplied minus 770. Remember, we found density of the liquid on the previous question, multiplied by G, which is 9.81, multiplied by, we are told the dimensions of the cross-sectional area. Cross-sectional area is this, and the length of the cylinder is this. So knowing those, we multiply them like that. This will give us the tension as 0.42. So we have found our tension as 0.4.